So today we're going to be talking about the law of sines, and so I guess the first thing is let's just mention what the law. The law of sines is a relationship between three sides of a triangle and the three angles of it. I label my angle A, B, C, and the opposite sides A. Notice that capital A for the angle, opposite side little a side. Side B is opposite angle B, and side C is opposite. I have the I'm so we're talking about the law of sines. Law of sines is a relationship between the three angles and three sides of a triangle, where every angle is labeled with a capital letter that corresponds to the opposite side being labeled with the same letter but in lower. There are some books that switch that, but I think this is pretty common that angle, this is the opposite side, and they say the same letter, but one is capitalized and one is lowercase. Law of sines is stated. So sine of angle A divided by the length of side A equals the sine B divided by the length of B, which equals the sine C divided by the length of B. And if we think about taking a triangle, let's take these two sides and fix their length. If I expand the angle between, the side is going to grow as the angle grows. So if I take the same length, probably this angle grew from the original size to the current size, and the length grew from its original size. And as that angle can grow, the opposite side will also. So when we look at this fraction, as the angle gets bigger, the sine will also get bigger until we hit 90 degrees. And the length of the opposite side will also grow. That keeps this balanced so that this fraction continues to equal these even as the angle side are changing. Once we hit 90 degrees, sine no longer increase, but also the length of that opposite side begins to, well, it doesn't increase fast. So how this, and let's do a problem with, I'm not going to prove the law of sines in. Oh, I rest my hand on the drawing tab. So we have this picture here, and I think it's actually So we want to figure out for this one how tall the building is. So we have this triangle that starts up. We have this triangle that starts up here. And we know that this distance and this distance, sorry, this position and this position are 150 feet across, or away from each other. And we know that the angle changed as we were aiming our eyes up at the point on the top of. So this gives us a triangle. If this angle is 48 degrees, that means that this angle is going to be 180 minus 48 degrees. Straight line. Straight angles add up to one, or two angles that add up to a straight angle add up to one. This here is going to be one. Get so. Hmm. So this is 132. This is 35. Means this angle up here we also know. But we're looking at this. Angle is 180 minus 90. 90 minus. Side is this angle. Big triangle. So that 35 x that what might have to um I guess if we found this side, then we say that 90 side are angle side opposite, and that would give us this angle with the side we're looking for, and this angle with a side that we. Let's do that. Hold this. I know that sine 13 degrees over 150. This angle is opposite this side. You need kind of diagonal triangle. That has to equal 132, sine of 132 over long side of the scale. Formula and solving for y, we're going to get y equals sine of over degrees. That'll be y value. Then we can use here we get sine 90 degrees over y is Now, sine of 90, get 1 over y equals x. Solve this. X I times y down here. B 5 degrees. This is going to be our final answer. Plug that into a calculator. $32 times the sine. 5 degrees divided by the sine of let's see if Wolf Alpha likes that. It gave me x equals point 7. How far we have to do this? Round to the foot. So roll down to the next problem. So it says fire towers A and all like. And I know that there are people who draw better. I kind of like it. Solve this problem. It says that the fire towers are 10 miles apart, and a ranger at fire tower A spots a 42 spots a fire 42 degrees north of tower B. Rangers at fire tower B spot the same fire 64 degrees from tower A. How far tower A is the fire? Looking for this. Know that sine of 64 degrees over x has to equal sine of, well, this over this length, which we don't know, or this angle, don't know, divided by 10 miles. And you might think, well, we don't know a side and we don't know an angle, so how do we solve this? But if you know two angles for a triangle, then you can find the third by subtracting from. Get 180 or 160 minus 42 gives us 64. 11 minus 7. So this is sine of 70. That's this over 10 miles. Solve x is 10 times the sine of 4 degrees over the sine 70, 70. That we type that into a calculator to get our answer. Next one. Next question. We have a ladder. Have window at the ladder. Told that so you've been asked to climb a ladder to the window because of hurricane. The building is at an 108. Yes, I should. Okay. So have this angle is 108. Angle between the building and the top of the ladder is 20. You place the ladder 10 from the building. Says the law of sines to figure out what length of ladder. So if I know this side and I know this angle, and I'm looking at this side, that gives sine of 20 over 10, sine of 100 over x. Multiply, we get x equals n sine of 1 over sine. Again, we can plug into a calculator. I do that at me that the ladder is 7 are as round to the 10th, that rounds to 7 feet. Pilot is flying a small plane over a straight. Cyclists that are 3.7 miles apart. Determines the angle of depression. He determines the angle of depression to be the person biking north, be the left one in the when I post. Go. He determines the angle of depression to the person biking north to be 9 degrees. To be 67 degrees, and the person riding south be 59 degrees. Determine the distance labeled X in the picture from the plane to the person biking south. So, I have this picture here. Um, so if this is 7, then that means drop a line here. That means this angle is going to be complement of 7, which is 23. And this angle is 59. That means this one is going to be 1. Total angle 4. We also know that if this is 59, this is also 1 is 67 by the alternate. So our triangle looks like this. 7. This is 9. One is sure that adds up correctly. 54 plus 59 is 130. Plus 7 gets 120. Plus 6 have that. We're told this side is 3.7. We want to find distance plane and the person biking south. It says the south one is the one with the angle 9. We want to figure out this. Now, I've been writing the signs on the top and the sides on the bottom. Have to do. Like, I can take this equation, cross multiply, and then divide by the signs on both sides. And I'll get b over sine of a over the sine a. So I could write it this way or a bunch of other ways. But if I'm solving for a side, it makes sense to put unknown side on so that I don't have to fiddle around as much with the variable to try and solve it. But triangle, we have x over sine of 7 degrees equals 3.7 miles over that gives us x 0.7 sine 7 degrees over I can plug that into a calculator. Not 50. Sine of 50. Plug that into a calculator. If I do that, I get 4. Or not 3. 7 sine of 67 degrees over the of 4 degrees. This gives me 4.09. Oh, and that's it. That homework. Let's open up another one. I'm going to take a look at the grades and figure out alignment is the one that was based on having the. Okay, found one that we work on. Had some. I've, by the way, opened the book for higher school. So, question Platonic solids. Question one. It talks about regular polygons and irregular polygons. Um, Questions are what makes a polygon a regular polygon, and sketch 6 different regular polygons. And so gives you a bunch of polygons. I'll send those. Oh, so it wants you to figure out like what's the same about the regular polygons that are not true irregular polygons. And you can pause now and think about it if you don't know the definition of a regular polygon and you would like to try and figure it out on your own. Because right now, I'm going to tell you the regular polygons, they all have equal sides. So notice that this side is not the same length. This side, that means regular. They also have all of the angles are equal. So this one, not regular. They're also convex, which is a little bit more complicated to state, but basically, if I pick any 2 points inside of the shape and draw a line between them, that whole line segment is going to be inside the shape. For any 2 points that I pick, connect them, they're always going to be inside. Now, you could argue um, so this here is not regular because it's not convex. Could argue that this angle is not the same, therefore not regular, and that is a valid way of this angle, not that one, not regular. But suppose we take this shape here and we go all 90-degree corners, making sure that side is equal. I know I didn't draw it that way. But you can imagine how it would all of the sides that I marked were. So even though this angle is 90 and that angle is that angle's 90, that angle's um there are two ways that this is not a regular polygon. One is that person might go and say, well, only the interior angle matter, saying the angles are the same. And this is a 270-degree interior angle, and this is a 90-degree, so they're not. And that's one way of rejecting it. The regular has to be interior angle all the same. But if someone just said all the angles are the same, you could potentially argue that these exterior angles are, so the angles are in fact the same. At which case, having the extra hypothesis convexity, meaning that take 2 points in the shape and draw a line, the whole line segment has to be inside the shape. This is not convex, and so not regular. And the next thing it asks us to draw 6 regular polygons, 3 non-regular. Well, I guess I drew a non-regular. I'm gonna leave the drawing up to all seen so far that I won't see. What makes a solid? What makes a solid a regular Platonic solid? Well, it's going to be the same thing. You want all of the angles same. The angle is the same. That one, that one. And then we want all the sides the same, so that's the same length as that, is the same that as that. We also want all the faces to be. So this cube, we want, I have a square face, another square face, another square face, and 3. Those 6 faces are all the size, they're all the shape, they have the same angles, they're all congruent. So that perfectly characterize a regular polyhedron. Polyhedron. I think that if you that those requirements, like I still have to talk about either interior and convexity. That may throw the wrench, but yeah, for all properties of of regular congruent faces, angles between faces, and side lengths. How many faces, edges, and vertices are there in a cube? Well, let's count. There are 1, 2, 4 edges on top, 1, 4 edges on the sides, and 1, 4 edges on the bottom. So edges, there are 12. Places where we have 1, 2, 5, 6 are vertices, and faces have for a tetrahedron. Tetra means 4. You want a hedron, 4 faces. So look at this. Number of vertices are 1. Number of edges are 1, 2. Number of are again 1 here in front, 1 here in front, 1 underneath, 4 faces. The next one says explain why the cube and octahedron are duals of each other. So dual is interesting property. Each of the regular polyhedrons have a dual. You can make a dual existing polyhedron. You can actually make duals of any shape. Here's the idea in two. So if I look at, say, if I look at draw some. Okay, I have some shapes here. The dual of this is I put a dot in the middle of each of my shapes, and I connect the dots if the two shapes share a side. So this shapes and this shape have a side in common, so I connect their dots, connect these dots for this. There is no side in common between this triangle and the square alone, but there's a side in common there. You have a side in common there, and square and the last triangle have a side in common there. Dual is this pentagon. One more. They have triangle here. They have hexagon here, square here, and lots of different. This don't even have X shape. Take this, and I want to make the dot 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 dot. Now I go this polyhedron next to that one side, and there, and there, and so my dual is going to look like now. For polyhedra, it's a little bit harder because we have an extra, but it's going to put a dot in the center of each of the faces. Down here on the bottom, back, there on the side, connect them all. End up, this dot is going to connect to there, there, connect. Those will connect. Ones will connect. And then each of the four top, the two sides and the bottom, are going to connect back. And if we pull this shape out, it's going to be the dual of the sided die. We know that the vertices on a polyhedron correspond to the faces of the dual. So top vertex, it goes with the top side. Bottom vertex goes with the bottom side. The sides, the corners correspond to face. So the four of the corners here correspond to the right side of the left. So if we look at the five platonic solids, tetrahedron, hexahedron, octahedron, then we have the dodecahedron. Hey, let's. Can't draw. We have the dodecahedron. 12-sided. So there are five of them, and the octahedron, the cube, the dodecahedron, icosahedron, and tetrahedron. That's kind of neat. Okay. Um, Question 5 says, suppose you have models of platonic solids that are not transparent. Lower sketches, identify each one and explain the perspective from the solid as viewed. You're going to say, like, this is, you're going to look at each of the pictures and you're going to decide, well, what shape is it? And am I looking at an edge, a corner, or a face? Let's get that. So I have this here shape. Have this shape, and this shape, and we want to figure out what are we looking. This one is actually. You might think, oh, it's a problem is that the way this is drawn makes. But time we have today, so I'm gonna have to let you continue to work on that. Send me questions, have them, and I will do another stream on Monday. I might be able to fit tomorrow. I'll send you. Have a great day. I will see you later. Luck on the home.